It's not an exaggeration to say that object-oriented programming, or OOP, has revolutionized the way we write code. It's the programming paradigm at the center of the mobile apps we use every day, as well as the massive enterprise systems that underpin the entire tech industry. You could say that it's the single most influential programming paradigm in modern software development, and a concept that you absolutely must know in your programming journey. So let's break down the fundamentals of object-oriented programming from the ground up, using plenty of real-world examples to get there. Then we'll unpack OOP's indispensable role in helping us write cleaner, scalable, and more efficient code, an understanding that will serve you throughout your entire career. Start your engines. If you've come this far, you're probably familiar with popular programming languages like Java, Python, C++, and JavaScript. These are all object-oriented programming languages. But to really understand how these languages actually work, we need to start with OOP's two most foundational concepts: objects and classes. What makes object-oriented programming such a powerful tool is that it's designed to mirror the real world, where everything around us is an object, each with its own attributes and behaviors. We'll get more into objects in just a second, but I actually think it's helpful to start with classes. Take the example of a car. In OOP, a class acts as a sort of blueprint for everything that comes after. So in this example, you might have a car class that defines specific properties inside of that class, like color, model, and engine type, along with specific behaviors like start engine or accelerate. In our example, the car class has two properties, color and model, and one method, start engine. This method represents the action of starting the car's engine, which can be invoked by any object created from this class. So now's a good time to talk a bit more about objects. Once the blueprint or class is set, you can create multiple instances of it, known as objects. Objects are the actual instances created from a class. Each object is a specific instance of the class and can have unique values for its attributes. For example, while the car class provides the general blueprint, there might be different objects created from this class. For example, two objects might be my car and your car, where my car is red in a Toyota Corolla and your car is blue and a Honda Civic. Or to put it another way, OOP allows the creation of objects that can have unique characteristics, despite being based on the same blueprint. Here, my car is an object created from the car class. It has a color of red and a model of Toyota Corolla. When we call the start engine method on my car, it prints engine started. This demonstrates how objects can have different values for their properties, making each instance unique, even if they share the same class. Let's move on to another concept that is integral to OOP: methods. Methods are functions defined within a class that describe the actions an object can take. For example, a start engine method in a car class represents the car's ability to start its engine. OOP allows these objects to interact within the system, each behaving according to the structure and rules defined by their class. This organization makes it easier to model complex systems, like a fleet of cars in a simulation or a network of users in a social media application, because we're able to break the system down into manageable, reusable pieces. Let's go back to our car example. The car class has a method called start engine. This method represents the action of starting the car's engine, which can be invoked by any object created from this class. Methods bring objects to life by enabling them to perform actions. Each object is a self-contained unit that encapsulates both data and behavior, making the code more intuitive and aligned with how we naturally perceive the world around us. Therefore, by organizing code around objects, OOP helps developers create software that is a lot more modular, scalable, and easier to maintain. Now, let's explore the 4 core principles that make OOP so powerful: inheritance, encapsulation, abstraction, and polymorphism. We'll also explore how these concepts relate to real-world examples and look to some basic code templates to start putting what we're learning into practice. Let's start with inheritance. Inheritance allows a new class to inherit properties and methods from an existing class, sort of like how a child inherits genetic traits from their parents. Inheritance is such a powerful concept because it makes it a lot easier for us to build new functionalities without having to start completely from scratch. Consider the organizational structure of a company. At the top, you have a general employee class, which accounts for every individual at the company. Every employee in the company shares common attributes like name, salary, and employee ID. However, each role within the company, such as manager, developer, and designer, has specific responsibilities and behaviors. For instance, the manager class might have a method assign tasks, the developer class might have a method write code, and the designer class might have a method create design. These subclasses inherit the common properties from the employee class, such as name and salary, but also define their unique behaviors. Inheritance allows you to create a hierarchy of classes that share common features, while allowing for specialized behavior in child classes. The parent class, also known as the superclass, contains the general attributes and methods. Child classes, or subclasses, inherit the same attributes and methods as their parents, but also have the ability to introduce additional features or override existing ones. Let's look at a code example to see how inheritance works in practice, using the company structure as our model. In this example, the employee class is the parent class that defines common attributes like name and salary, and a method, getDetails, to display these details. The manager, developer, and designer classes inherit from employee, gaining these common features. However, each subclass also introduces its specific methods: assign tasks for manager, write code for developer, and create design for designer. This structure allows us to reuse code efficiently while also catering to the unique needs of each role. Inheritance not only simplifies code by allowing reuse of common attributes and methods, but also promotes a logical and organized structure within your program. Just like in a family tree where traits are passed down from parents to children, in OOP, inheritance ensures that you can build on existing code, making it easier to maintain and extend. Let's move on to encapsulation. Just like a turtle's shell protects its body, encapsulation in object-oriented programming safeguards an object's internal data. It ensures that data can only be accessed or modified through specific methods, maintaining both security and simplicity. This protective layer makes the object easier to manage and interact with, just as the shell shields and shapes the turtle. Consider a medical record system where each patient's data is extremely sensitive and must be handled with the utmost care. A patient's medical history, treatments, and personal information are encapsulated within an object representing that patient. Access to this data is strictly controlled. Only authorized methods can update or retrieve the information, ensuring that the data remains secure and consistent. In this system, doctors and medical staff interact with the patient's data through specific methods like update medical history or get medical record. They cannot directly alter the internal data, such as the medical history or personal details, without going through these predefined methods. The encapsulation ensures that all interactions with the data are validated and tracked, protecting the patient's privacy and the integrity of the information. Alright, so how does encapsulation actually work? In OOP, languages bundle data, which we call attributes, and the methods that operate on that data into a single object, which is created from a class. Public methods are accessible from outside the class and allow other objects to interact with the encapsulated data in a controlled manner. Private attributes are hidden from outside access and can only be modified by the class's own methods, ensuring that the internal state remains consistent and protected from unintended or unauthorized changes. Back to our example. The patient class encapsulates the patient's medical history attribute, making it private. This means that it cannot be accessed or modified directly from outside the class. Instead, we use public methods like getMedicalHistory to retrieve the medical history and add medical records to update it. This ensures that any changes to the patient's data are made in a controlled and validated manner, protecting the integrity of the data. In summary, encapsulation is like a protective shell around your data. By controlling access through specific methods, It safeguards the internal state of an object, making your code more secure, reliable, and easier to maintain. Just as a turtle shell protects it from external threats, encapsulation shields your data from unauthorized or accidental changes, ensuring that it remains safe and consistent. On to the next core principle of object-oriented programming, abstraction. Imagine you're sitting behind the wheel of a car. You interact with the dashboard, turn the steering wheel, press the gas pedal, or use the brake. A car is a complex system with tons of intricate component parts, but you don't need to understand each system in order to operate the car. For instance, when you press the brake pedal, you don't need to know how hydraulic fluid applies pressure to the brake pads, or how the anti-lock braking system modulates pressure to prevent skidding. All you need to know is that pressing the pedal slows the car down. This is abstraction at work. In object-oriented programming, abstraction functions in a similar way. It exposes only the necessary parts of an object's functionality to the user, like the gas pedal or the steering wheel, while hiding the complex implementation details, like the engine or braking system. For example, when you're using a car object, you interact with methods like accelerate or brake, without needing to see or understand the internal code responsible for handling speed calculations or fuel efficiency. Just as a driver doesn't need to be a mechanic to operate a car, a programmer using an object doesn't need to know the underlying implementation, only how to interact with the object's exposed methods. Here's another example. Imagine withdrawing cash from an ATM. You interact with a simple interface. You insert your card, enter your PIN, select the amount to withdraw, and the machine dispenses your cash. The entire process feels straightforward, but behind the scenes, complex systems are at work, checking your account balance, communicating with your bank, and recording the transaction. This is another great example of abstraction. The ATM provides a simple, user-friendly interface that allows you to complete your task without needing to understand the intricate banking systems that make it all possible. The complexity is hidden from you, the user, so you can focus on the task at hand, getting your cash. In programming, abstraction allows developers to create simple interfaces for more complex underlying code. This is done by defining abstract classes or interfaces that provide a high-level blueprint for other classes to implement. An abstract class is a class that cannot be instantiated on its own and is meant to be subclassed. It often contains abstract methods that are declared but contain no implementation. Subclasses of the abstract class must provide an implementation for these methods. An interface is similar to an abstract class, but is even more restrictive. It can only contain method declarations, and those methods must be implemented by any class that uses the interface. Back to our ATM example. The payment class is an abstract class with two abstract methods, process payment and get transaction details. These methods are just placeholders without any implementation. The credit card payment and PayPal payment classes are concrete subclasses that implement these abstract methods, providing specific behavior for credit card and PayPal payments, respectively. The complete transaction function accepts any object that is a subclass of payment and uses the abstract methods to process the payment and retrieve transaction details. This function doesn't need to know the specifics of how each payment method works. It just interacts with the abstract interface provided by the payment class. To recap, abstraction is all about creating a simple, high-level interface that hides the complexity underneath. This not only makes your code easier to use and understand, but also makes it more flexible and scalable. By focusing on what an object does rather than how it does it, abstraction is a key aspect of OOP that helps us create cleaner, more maintainable code. Finally, let's look at the fourth core principle of OOP, polymorphism. Polymorphism allows methods to be used interchangeably across different objects. Think of it like a Swiss Army knife, one tool with many functions, each serving a different purpose depending on the situation. Imagine you're using an online store and you have multiple payment options: credit card, PayPal, or cryptocurrency. From your perspective as the user, the payment process is pretty straightforward. You select your payment method, enter the necessary details, and confirm the payment. But behind the scenes, the system is handling each payment type differently. In a payment processing system, you might have a single method called process payment, which can handle different types of payments. Despite the varying processes behind credit card transactions, PayPal, or cryptocurrencies, the user experiences a uniform interface. This is a great example of polymorphism. The same method is used, but it produces different behaviors depending on the object calling it. Polymorphism in OOP is typically achieved in two main ways: method overriding and method overloading. Method overriding occurs when a subclass provides a specific implementation of a method that is already defined in its superclass. The overridden method in the subclass is used instead of the one in the superclass when the object is of the subclass type. Method overloading allows multiple methods with the same name, but different parameters in the same class. Depending on the arguments passed, the appropriate method is called. Back to our payment processor example. We have a base class payment with a method process payment. Each subclass, credit card payment, PayPal payment, and crypto payment, overrides this method to provide its specific implementation. The process any payment function demonstrates polymorphism by accepting any payment method object and calling its process payment method. This way, the same function works with different types of payment objects, each executing its own version of the method. Just like a Swiss Army knife adapts to different tasks with different tools, polymorphism allows your methods to adapt to different objects, making your code more dynamic and scalable. Polymorphism is such a powerful tool in the OOP toolkit because it enables us to seamlessly add new classes and override methods without changing the code that uses these classes, which goes a long way towards enhancing the flexibility and extensibility of our code. Now that we've covered the 4 core principles of object-oriented programming, let's move on to another important topic: the relationship between classes. Class relationships are fundamental to how different components of a system interact and work together. By defining these connections, we can create software that's modular, reusable, and easier to maintain. Let's explore the main types of relationships between classes and see how they help structure a well-designed system. Inheritance, our first core principle of object-oriented programming, represents an is-a relationship between classes. It allows a new class or subclass to inherit properties and methods from an existing class or superclass. For example, if you have a vehicle class and you create a car class that inherits from vehicle, the car is a type of vehicle. The car class will inherit common properties like wheels and engine from the vehicle class, but it can also have its specific properties like trunk size. Association represents a has-a relationship between classes, where one class is associated with another. It's a broad term that can include different types of connections between classes. Let's look at 2 key types of association: unidirectional association and bidirectional association. In unidirectional association, one class knows about the other and interacts with it. In bidirectional association, both classes are aware of each other and can interact with each other. A library class might have an association with a book class. The library has books, so there is a relationship between library and book. Aggregation is a specialized form of association that represents a whole-part relationship between classes. It is a weaker relationship compared to composition, meaning the part can exist independently of the whole. Imagine a basketball team. A team class might be composed of multiple player objects. Even if the team is dissolved, the players can still exist independently. They may belong to other teams or simply be individual players. Composition is a stronger form of aggregation where the part cannot exist independently of the whole. When the whole is destroyed, the parts are also destroyed. Consider a house class composed of room objects. If the house is demolished, the rooms do not exist independently. They are integral parts of the house and therefore cease to exist along with the house. Dependency is a relationship where one class depends on another class to function. A change in one class may affect the other. For example, a car class might depend on an engine class. The car needs an engine to run, so there is a dependency relationship between the two. Let's quickly recap the key relationships between classes in object-oriented programming. Inheritance has an is-a relationship where one class is a subtype of another. For example, car is a vehicle. Association represents a has-a relationship, where one class is associated with another. For example, a library has books. Aggregation has a whole-part relationship, where parts can exist independently. For example, a team has players. Composition has a strong whole-part relationship, where parts cannot exist independently. For example, a house has rooms. Finally, dependency is where one class depends on a different class. For example, car depends on engine. Understanding these relationships is critical to designing robust and maintainable object-oriented systems. We must be able to clearly define how different components of the system interact and depend on each other in order to ensure seamless communication, minimize complexity, and promote code reusability and scalability. To this point, we've explored the fundamentals of object-oriented programming using a few examples to help illustrate the core concepts. Now it's time to look at the real-world benefits of OOP in modern software development. Listen closely because these benefits will remain useful throughout your entire coding journey. You've probably heard the term modularity, maybe in the context of creating modular code. Modularity is one of the key strengths of OOP, and it's really important to talk about here. As we discussed earlier, in an object-oriented system, code is broken down into small self-contained units known as objects. Each object represents a specific part of the program with its own data and behavior. Imagine a construction project. Instead of building the entire structure as one piece, different teams handle separate parts. Think plumbing, electrical, and carpentry, with each team working on their respective modules. In OOP, each object handles a specific aspect of the program, making the overall system easier to develop and troubleshoot. This focus on modularity means that developers can focus on one object at a time without worrying about the entire system. If you need to update or fix a bug, you can go directly to the relevant object, make the necessary changes, and then test it independently before integrating it back into the system. A related advantage of OOP is reusability. This one's pretty straightforward. All it means is that once you've created a class, you can reuse it across different parts of your program, or even in different projects. Consider a car manufacturer. They often use the same engine design in multiple car models. This reuse of a proven design saves time and resources. Similarly, in OOP, a well-designed class can be reused across various programs, reducing the need to rewrite code from scratch. For instance, if you've written a user class for managing user accounts in one application, you can easily reuse this class in another application, whether it's a web app, a mobile app, or a desktop app. This reusability leads to faster development, consistent behavior across applications, and fewer bugs. Now let's move on to something that's absolutely critical in today's tech landscape: security. Object-oriented programming enhances security by protecting data through encapsulation. Remember our turtle shell? Encapsulation means that an object's data is kept safe inside the object and can only be accessed or modified through well-defined methods. Imagine a bank vault where valuable assets are stored. Only authorized personnel with the right keys can access the contents. In OOP, an object's internal data is secured, and only authorized methods can interact with it. Now for a technical example. Encapsulation helps prevent accidental or unauthorized modifications to an object's data. For example, in a banking system, you wouldn't want an outside entity directly altering a customer's balance. Instead, you encapsulate this data within an object and provide specific methods like deposit and withdraw to safely manage changes. Maintaining and updating code becomes much simpler with OOP. Since everything is organized into objects, changes in one part of the program can be made independently without affecting the entire system. Think of a well-organized library. If a new book arrives or an old one needs updating, you can easily locate it in its specific section without disrupting the entire collection. In OOP, you can make changes to individual objects without needing to overhaul the entire codebase. Here's another technical example. Because objects are self-contained, you can easily understand and modify one object without worrying about unintended consequences in other parts of the program. This modularity leads to easier debugging, quicker updates, and more efficient management of the software lifecycle. To sum it all up, object-oriented programming allows you to build software that is not only well-structured and easy to manage, but also secure and efficient. Whether you're developing small applications or large-scale systems, OOP is there to help you create robust, maintainable, and scalable software. Which raises the next obvious question: how do you actually structure an OOP program? Structuring an OOP program involves identifying the entities you want to model, organizing them into classes, and then creating objects that represent specific instances of those classes. This approach helps you think logically about your problem and plan your program effectively. Take this example program. As a first step, we identified the key entities: book, member, and library. Then we created classes for each. Finally, we instantiated objects from these classes to simulate a simple library system. By following these steps, you can effectively structure and manage your code using OOP principles. And just like we did here, it's okay to start small. We've covered the basics of object-oriented programming, its core concepts, principles, and benefits. But this is just the beginning. To deepen your understanding, you're ready to move on to more complex topics like design patterns. More importantly, you're ready to start implementing OOP in different programming languages, maybe even starting to build your own projects using these concepts. If you're ready to level up your skills even further, we linked a few interactive online courses and projects below. Educative is a great place to actually get hands-on with the concepts we discussed today without any setup, downloads, or configuration. Well, we did it. Thank you for watching. If you found this video helpful, please like, please comment, please share it. And if you're interested in checking out more tutorials like this, go ahead and subscribe to our channel. Happy coding!